Hi, thank you again for the opportunity to present our work at this conference. My talk today is going to be about utilizing eye tracking to shorten the learning curve in robotic surgery, basically looking at what the surgeon can see. My name is Ahmed Ghazi. I'm an associate professor and director of the Simulation Innovation Laboratory at the Department of Urology in the University of Rochester Medical Center in Rochester, New York. So to start off, I wanted to kind of explain what an eye tracker, what eye trackers we use. They're head-mounted eye trackers to allow the movement of motion rather than the stable eye trackers. So they have two cameras. There's a camera that actually is recording your eyes or your pupils, and that is an infrared camera, and it records many things like pupil diameter and what we call pupil metrics. And eye movements. And there's also another camera, which is a head-on camera, which we have synced with the Da Vinci robot that allows us to actually look at the screen of where the surgeon is looking at, which is your gaze path. Going over pupil metrics real quick. So pupil metrics, or TEPR, is the task-evoked pupillary response. So it is the responses of our pupils to tasks or cognitive load. As you can see, our eyes move very quickly, and this is a response to cognitive load. And the saying that says we see things before we move, that is correct, because the eyes are closer to the brain. So it's an actual window into what the surgeon is going to do and what the surgeon is how the surgeon is going to move. This is opposed to gaze metrics, which shows where the eyes are looking at. Fixations is where we tend to, just like it says, fixate for a couple of milliseconds on certain objects that we're focusing on. And if you look at the picture there, the larger the circles shows the larger the duration of the fixation. Heat maps are a conglomerate of these fixations and our gaze path, and they kind of show where we are focusing on the most. So it's over a period of time. So for example, when you're driving, you can say you're focusing on certain areas in the console versus certain areas in the road ahead of you, and they tend to be color coded, and marketing has been using this a significant amount of time to figure out what attracts the users or what attracts somebody that's, for example, buying things in the supermarket aisle. We are interested in the cognitive component of that. So as we know, there are three components of cognitive load: intrinsic cognitive load, which is how difficult the task is; extrinsic or extraneous cognitive load, which is the impact of external factors on your ability to focus; and germane load, which is actually, it's weird that it's considered load because it actually is a good load. It is our ability to learn. It is the cognitive effort that we are using to learn or interpret certain things, which becomes very interesting to us in surgery. This is a quick example of my eye patterns, actually. And if you look at our pupil lobe, my pupil metrics, and you can, this is fast forwarded to show you how fast my pupils are moving. So this is a basic task on the simulator. It's suture sponge 1. It's something that I'm very familiar with. Sorry about that. And it's something where my pupils are really not moving too much. All right. Now, if you move along to something that's a little more difficult, which is suture sponge 2, so now the depth of the sutures are very different, and therefore I have to focus a little bit more. My pupils are moving a little bit more, but still my performance is way better. And then now we come to suture sponge 3, where my eyes are moving a little bit more, because not only is the depth of the suture moving, but also the location of the suture or the task is moving, and my pupil load is starting to go up, my pupil diameter is starting to go up. Then we go to tubes that involves, a series of sutures I should take, and you can see not only are my pupils dilating and closing, but also my eyes are moving. So my fixations are varied. The saccades, which is the duration between these fixations, is also being immense. But my score is still well over 95%. Now, this is an exercise I haven't practiced a lot, and I really don't like, and I personally don't think it's very well designed. So there's a frustration that comes with that. You can see that while I'm trying to get to these errors and trying to really pinpoint where the needle is, my eyes are, my pupils are dilating and constricting really quickly, while at the same time, there's these micro movements in my eye denoting that my fixations are happening on different levels. And you can see in the pupil diameter already that it's starting to go up significantly. So this is a prime example of what we're trying to do, and it's reflected also in my score. So what are the applications that we want to use? So if we look at gaze metrics, we've done a test or a couple of experiments in simulation. So these are the models that we make, and that's shown in my previous talk, where we had some experts and some novice deal with a bleeding vessel. So basically what they had to do is dissect this vessel out, and then when it starts to bleed, they have to suture it. You can very clearly see that the experts are very focused, which is in the bottom, focused on exactly where they're looking at, and their fixations are even more in the area of interest. And they're kind of looking at the periphery, but very limited. Look at the novices, which are on top, and these are pure novices. You can see that they're all over the place. They're trying to find their instruments. They're trying to find their needles. The fixations are really not focused in a certain area. They're all over the place, and the heat map is kind of distorted everywhere. So for a task where they have to focus in a certain area, they failed. But if we're looking also at a task where the surgeons tend to scan a wider area, you'll find that the surgeons are effectively able to focus in the middle, but also scan the periphery very quickly. This is also what we are trying to do with live heat maps. So we place a QR code within the vicinity of the eye tracker, and the eye tracker is able to give you real-time heat maps. So this is one of our simulated lymph node dissections, and basically what we're trying to do is trying to let them find the ureter. So you can see as the surgeon is moving down to the right, you can track their heat map in real time. So not only find out what they're looking at, but while they're concentrating on what they're focusing on at the same time while they're doing the task. So it becomes very interesting to look at that and really monitor where the surgeon is starting to focus and where the surgeon is in auto mode and they're starting to really get through. So even though there's a sectioning on the iliac vein there, they're doing it pretty quick because they know that there is nothing that over there is pretty risky. But when they get down to the area of the ureter, they tend to slow down, focus a little bit more, and scan the area. So this becomes a very interesting application. We did a very interesting study where basically we had two groups of people. One group was given a pre-recorded video, a simulated task of a surgeon's gaze metrics or gaze pattern. And we also had another group which actually got the instructions based on movement, hold the needle in a certain area, drive it in a certain way. So everyone got a valuation on a certain task. And then we randomized them into two different groups based on their task performance. And then we had a pre-learning area where each one was given the instruction, we either gaze instruction or movement instruction. Then we actually coached them where when they performed the task for the first 3 repetitions, they actually got feedback looking at their own gaze metrics and the expert gaze metrics, or looking at their own movements and comparing that to the expert movements. And then we actually did a stress test. So we had them go to proficiency and then did a stress test at the end to see how resilient they were. So this is an example of the actual gaze instruction. So the instructions are very focused on where the surgeon is looking rather than how the surgeon's moving. So the next one was actually movement training, where basically you're given instructions of how to handle this. And if you look at the trajectory here, you can easily see that the gaze training group from the very beginning, after the pre-learning, so from the very beginning, by just watching a video based on gaze patterns, they were able to outperform their contemporaries based on a movement instruction. And as they move through the first 3 repetitions, you can say that their trajectory is exponentially increasing compared to the normal trajectory of the movement group. They started to balance out while they were going to the 10 from the 3rd repetition to the 10th repetition, but you can say that the gaze training group always maintained a higher level average or a mean score and less errors compared to the movement training group. This is from the very beginning. And you can see that steep curve between 3 and 4 showing that we taught them significantly during that time where they were getting feedback. We also kind of noticed that target locking and instrument locking was something that they developed. So they actually adapted the gaze patterns of an expert. So experts tend to do the following. Experts tend to lock on the instrument rather than lock on the target rather than lock on the instrument. So when they're pulling the rail off there, as soon as they pull the rail off there, their eyes goes to the next target, which is the other hand, and then goes to the peg. And same here. As soon as they pull the peg off, they look at the other hand, pass it over, and then eyes shoot over to what is highlighted, which is where the ring should go, which is actually the target. Compare that to a novice, where the novice tends to kind of follow their instrument. So you look at what they're doing, they're grabbing the instrument and then moving along with the instrument compared to the expert who shoots right to the target. So this is instrument locking versus target locking. And it's known that expert surgeons tend to target lock while novices tend to instrument lock. And if you look at the bar chart here, you can say that at the baseline, the gaze training group did have a higher number of fixations meaning that they had more fixations on the target, which is either the arm or the flashing target or the needle itself. And then as they trained to the 10th repetition, you can see the gaze training group outperformed the movement training group. And during stress, they maintained that. So not only did they have the expert fixations or the expert gaze patterns, but they maintained it during a stress test, which is basically having to do the task while counting the number of bells that are happening in the background. Here you can see a good example of also using gaze entropy. So gaze entropy, which is how fast your eyes move between different targets, is actually something that can use to measure cognitive load. And you can see in the gaze training group, from baseline to proficiency, it fell all the way down, but it was also maintained during the actual stress test. While the movement training group continued to go down. Now, although that the movement training group stress level went lower down, but their actual beep count, which is the number of percentage of correct beeps that they had, was significantly more errors during that task. So they had less stress because they focused more on the beeping task than they did on the other task, while the gaze training group was able to divide their cognitive load equally between both tasks and maintained it at a certain level. I'm open to any questions any of you have.